28 people, I think. And then we do all that stuff in the beginning where they pull you out and talk to you, and then we have about 13 to 15 students attending now. It's kind of crazy, huh? I have no idea. Even if a student dropped, I couldn't tell you, but yeah, I mean, this is pretty normal. Okay, so it's a good thing, I think, because most of the people here are, you know, focused and in the right place. So, all right, let's. Yeah, most of you. Yeah. Not all. Most of.
Some of us are kind of like recruiting class, but when it comes to trying to do our own, it's just things coming out of here.
I'm gonna continue from where I was last time, and we talked about quite a few things. And this problem should kind of summarize the stuff we were talking about when it came to those extreme values or local maximums. Remember that? Right. Talking about that? Okay. All right. Global stuff. So here's a graph. And I believe that this graph goes down forever. Let's put an arrow on it. And let's answer these questions. First of all, what are the intercepts? So part A. When we say intercepts, there are two types. There's x-intercepts and there's y-intercepts. Anywhere where the graph touches the x-axis would be an x-intercept. So we are going to list out the x-intercepts which occur here, right? There. Here, and here. So we have three of them. Now, the way you list these is kind of, I'll give you a little flexibility here. You could list out the x's, like x equals this, 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 or you could list them as points, like ordered pairs. So let's see what this point is. 1, 2, 3, 4, 5, 6, 7, 8. So -8. So you could write this. X is -8, or where else?
-4.
-4 and 7. You could do that. If you don't like that, then you could write them out, you know, actually as points, like -8, 0, -4, 0, and then 7, 0. So those are 3 points, right? Either way. All right, how about the y-intercept? Do we have one?
0, -3.
So here, down 3. So you could write down, again, y is -3, or you could write down 0, -3. Either way. All right, what is the domain of the function? So it goes down forever, which means we're assuming it comes this way forever. So -infinity, we always have picture, don't we? We always have graph until we get here and it stops. So 3, 4, 5, 6, 7, 8, 9, 10. So the domain, part B, would be from -infinity to 10. Now, parenthesis or bracket there?
Bracket.
Bracket, because it does actually have a point at 10, right? Part C, the range.
-infinity to, let's see, 1, 2, 3, 4, 5.
So you're looking at y values, right? -infinity, and then it goes up. The highest point it ever reaches is here, which is 5. So I write that as -infinity to 5, in a bracket on 5 again, still, because it does reach 5. Just remember, these are x values. These are y values. D, where is the function increasing? That means where is the function going up, right?
From -8 to -infinity.
Yeah, we're assuming this goes down this way forever, so we're always coming up, right? Until we get... Yeah, I added the arrow.
I didn't see that arrow for a bit there.
Yeah.
Sorry.
No, it's all right.
I didn't see that.
Yeah. I don't know, are you looking off the notes?
Yeah.
Is there an arrow there?
No.
No, okay, so when I saw this, I said, I don't know if there's an arrow there, so I just put one.
Dot.
It's a dot, okay, so
Sorry,
we're varying a little bit from that.
apologize.
No apologies necessary. All right, you ready? So -infinity, it's going up until it reaches where?
To -6.
Right here, -6. So from -infinity to -6.
Bracket.
You could use bracket. It's okay to use bracket, but it's not wrong to do parentheses. All right, so there, is that the only place we're going up?
No.
Nope. Right here.
From 4 to 10.
4 to 10, right? So we're looking at x values. 4 to 10, same thing. You don't need to use brackets, union between them. And remember, these are x values, right? How about where the function's decreasing, part E?
From -6 to
So from an x value of -6 until we get to
-2.
-2, so -6 to -2.
2 to 4.
From 2 to 4. So from 2 right here there to 4, we're going down. Those again are x values.
Shouldn't they be brackets? Or does it not matter?
It does not matter.
Okay.
Does not matter. I know that that seems kind of maybe confusing why you wouldn't put a bracket. You know, so let me just address it. It has to do with the precise definition of what it means for a function to be increasing, which I kind of glossed over. This is the way it works. F is said to be increasing on an interval I if f of x sub 1 is less than f of x sub 2 when x1 is less than x2. That's the definition, which I could have come in here and I could have said that. And then everyone would have looked at it and gone like, what? Right? The basic idea of increasing is that it's going up, right?
Right.
All this is saying is that if I pick a point, let me look at a place where it's increasing. If I pick a point, like it's increasing right in here, isn't it? Let's say I pick a point called x1. And that x1, I want it to be less than x2, which means x2 needs to be to the right of it. Do you agree with that?
Yeah.
For it to be increasing, what we have to have is that when I plug x1 into the function, right, which would be that value, right? F of x1 is how low that is. That value, f of x1, has to be smaller than what I get when I plug in f of x2, which is up here. So is this point lower than this point? So as long as, so you have a point that is to the left of another point, right? This point is to the left of that one. Then the output of this point should be smaller than the output of this point. That's what it means to be increasing. The question though, why not parentheses bracket? The reason is because you need 2 points, all right, to even talk about increasing or decreasing. So if I put a bracket here.
Oh, okay, I see what you're saying. Because at that single point, nothing's happening.
Yes, exactly. At -6, I can't say whether or not a function is increasing at -6 or decreasing. I can't say that because I need to be able to pick another point to test with it. So if you put a bracket here, it's fine. If you put a parentheses, there's no harm in that also, because no matter what, I need at least 2 points. And there's an infinite number of points next to -6 that I could pick. So that's why we just kind of say, it doesn't really matter. Hope that answers kind of the question a little bit.
It answers why sometimes you use the brackets.
That's right. In the domain, we can't avoid that, because with domain, the function is either defined there or it is not at that point. So that's different, because we don't need 2 points to talk about domain. All right, now this is f, right? Where's the interval or intervals where the f is constant? So from here to here, which was -2 to 2. So -2 to 2. All right, G. Local maximums and minimums. So let's identify these. Local maximums and minimums. Let's start with local maxes. Local maximums. Where?
-6.
1, 2, 3, 4, 5, 6. -6,
-6, 2.
2. -6, 2. That point is a local maximum. It is the highest point in this region, isn't it?
Yes.
Okay, so this is a local maximum. We'll list it as a point. -6, 2. This is a point.
10.5.
And 10.5, where's that? Oh, at the very end, right? Because the function actually stops, that is the highest point in that region, isn't it? So 10.5? 5, okay. See, this is the one thing about mathematics at this stage that I've always said is a problem. And that's the fact that we write points the same way we write intervals. Right?
That is true.
I mean, that's like a huge, I think a huge mistake that we did as mathematicians when we were, I'm not taking the blame for it, don't blame me because it's not my fault. But like, you know, if I write 2, 3, just like that, and I ask you what that is, you don't know if that's a point, you don't know if that's an interval, right? Is that everything between 2 and 3? Is that x value 2, y value 3?
So you would assume that it was that particular coordinate.
That's right. So it's all in the context of what's being asked. If someone's asking for a local maximum, then you can't have an interval, wouldn't make any sense, right? So that must represent a point. But notation-wise, it's bad. Okay, are those the only local maximums?
Yes.
Yeah, agree? Okay, minimums, local minimums.
4.
Yeah, right here. So 4 out, -5 down. That's a point. Is it -5? Yeah. Okay, so 4, -5.
What about where the 2 points were the constant?
Where the 2 points were what?
The constant?
Okay, so that's a good question. Are these 2 points local maximums or local minimums? Or all these points? How about this point right here? Is that the highest point around it?
No.
Is it the lowest point?
No.
No?
Technically, you could say both are true if you're being a smartass.
That's right. And in calculus, we do say it's actually both a local maximum and a local minimum. But in this class, we are going to stick to things that are obvious, which are like this one and this one. When you get to calculus, you'll actually see that, look, there, every point here, between here and here, every point is a local maximum, every point is a local minimum.
So then you're going to have an interval for that if you're actually labeling
Then you
it.
would have an interval. So that's why we're
That's
not
what
going to
you're
mess
saying.
with it, yes.
For the sake of the test, we would just leave that alone.
I won't even throw a constant in there because I don't want there to be any confusion, all right?
You know you have us that are like, oh, well, this.
Yeah, because very seldom do we have functions that behave like this. A lot of times we have this curvy stuff happening, but not often does it go and all of a sudden flatten out and then just start going again.
It's more like a data plot more than so like a function.
Yeah, this is more like what we call a piecewise or step function where it changes. Like you do something for a while and then it switches to a different function, then it switches again. All right, got the local max, local min, we good? Okay, how about global maximum, global minimum?
10.5.
So do we have a global or just absolute maximum, the highest point on the curve? Yep, this is it right here. So the global max is going to be the point 10.5. And the global minimum,
This is infinity.
Negative infinity. Negative infinity.
what do y'all think? Negative infinity?
Yeah, because
That's supposedly you're supposed to be going completely down
Or is
until
there-
you
Never stopping,
Or
right?
is
That's
there
what that
no
arrow...
global minimum because it never stops.
That's a good question. That's the question we should be asking. Do we say negative infinity? Or is it that there is none because it never stops? What do y'all think?
I think for the purpose of this exercise, you should put negative infinity.
Yeah, that's right.
You
But
think he's
also
right? Okay.
But
So
for the purpose of this exercise.
here's the thing. Infinity is not a number.
It's a idea.
It's a concept. It's an idea. So when we talk about local maximums and local minimums and global maximums and global minimums, we're talking about concrete numerical values, right? Do you have a highest point on the graph? Yes. The highest y value is 10. It happens when x is 5. Do we have a lowest one? No, we don't. And we can't say negative infinity because even if we did, we wouldn't be able to tell you where it happens, right? So none. You could say empty set. You could say none. And I'll take any of those because it's a point, right? It's not, we're not asking for a set. So this wouldn't necessarily be appropriate, but I would take any of those because it means you understand that there is none. There is no global minimum. Okay?
Negative infinity.
Yeah, negative infinity, you wouldn't want to do that. Don't put negative infinity, negative infinity.
So let's say it was going up,
Forever?
then it would just, the maximum would be,
You wouldn't have one. You mean if this was an arrow going this way again, then you would have no, these would both be none. And when you think about that, there are a lot of functions that don't have either one. Like if you've studied cubic functions, that's what a cubic function looks like. They don't have global maximums or minimums. But parabolas, which we will study in more depth, right? All parabolas have a local minimum and no global maximum, or if the parabola opens downward, it has a global maximum but no global minimum. That's how parabolas behave. But once you get past the parabola, it gets more complicated. All right. This good? Okay. Let's move on. Feeling okay there, Ariel? Ariel? Yes? You know why I know your name so well? I had my 19-year-old niece come live with us this past year. She wanted to come to school and then go off to A&M. And she was a pain in the ass. She was a pain in my ass. I shouldn't be recording this. I should actually turn this off. But, so, man. She moved. She went back to live with mommy and daddy. She couldn't handle my discipline. She couldn't handle me getting mad at her for not bringing her trash down from her room once a week. I'm not bitter. All right, where are we here? We're done with this. Okay, average rate of change. So anytime we have a function, all right, does not matter what the function is. If you take 2 points on that function and you connect them with a line, then the slope of that line is the average rate of change. Does this look familiar to you? Have I shown you this picture before?
Yes, yes.
I have, right? We used this when we were doing the difference quotient, right? The only difference between this picture and the difference quotient picture is this. With difference quotient, what I did was I picked some value here which I called x. Then over here, I picked something and I said that this would be x plus h, good. And then I did my thing, right? The only difference between that and this is that instead of someone coming in here and saying x and x plus h, they decided to call this a and they decided to call that b. So this point up here is the point a, f of a, and this point over here is the point b, f of b. And if you want to try and find the slope of this line, then it's going to be rise over run, right?
Yes.
Which would be the difference in the y coordinates. Isn't that the difference in the y coordinates? F of b minus f of a. Over the difference in the x coordinates, which would be b minus a, right?
So that's the point.
This is the formula for finding the average rate of change of a function. So this function changed. When you go from a to b, it changes, doesn't it?
Yes.
This slope gives you the average rate of change. If I was more interested in knowing the instantaneous rate of change, like how fast was it changing right there, I would have to slide this point over, and that's what we did with the difference quotient from before, right? But if you don't care about sliding the point over, then this is just called the average rate of change of a function. That's the formula for it. That's the slope. So we can look at a function here, and for this example, what we're trying to do is just get some of this notation down. Let me blow this up so you can see it a little better. So we have a function, f of x equals 3x cubed. Find the average rate of change from 0 to 3. So in our formula, what's the 0, what's the 3 in the formula? Which letters are there? Mind if I slide through? I need to get another. Oh, wait, never mind. I think I have markers in here. I erased the formula we're using. Right, it was f of b minus f of a over b minus a. Okay? That's what we're going to use. What's a? What's b?
0 would be A and root would be B.
Yep, that's it right there. So now what we have to do is just evaluate this.
So pretty much plug it in and solve for fx.
I'm going to plug in and I'm going to get a numerical value. F of what? B. So f of 3 minus f of a, which for us is 0, over 3 minus 0. And now I actually have to plug these numbers into the actual function. So when we plug 3 into this function, what do we get? That's our formula that we're using. This is the work for this. So what is 3 in here? What do you get? 12? Yes? So you could just plug 3 in, right? 3 cubed is 27. 27 times 3 is... No.
Square, not cube.
Okay, so 81 minus 15, which is...
This reminds me of the whole x plus h thing.
Pardon?
It reminds me of the x plus h.
Yeah, but it's not so bad because all we're doing is plugging a number in, which is much easier than plugging in.
Okay, I just changed my thing from cubes to square root cubes at 66.
Okay. I'm just curious. Is that something I'm allowed to do?
Yes.
Look, everyone should be able to plug 3 into this without a problem, okay? But am I allowed to do that?
Yes.
Okay. Plug 3 in right here. What do you get? 9 times 3, right? 9 times 3 is 27 minus 5? 22, right? That's 22 times 3, 66. Just another way of getting the same result, right? 66 minus, oh, this one's nice, f of 0 over 3. Your answer is 22, right? 22. Questions? Graphically, here's what just happened. That's the actual graph of the curve that we're talking about here. That's the graph right there. We picked a point, it was 0, right? Which is this point. Then we picked a second point, which was at 3, which is, oops, that's not 3. Move it over. Oops. There it is, up there, right? And we tried to find the rate of change, which is 22. That's what we got, which represents the slope of that line connecting those, right? That's what we have. Now, what's the next part of this? They want to do it from -1 to 2. So all you would do now is what? Change this -1, 2, and then redo this formula, right? Now, I'm not going to do it, but let's just look at what we would get, okay? I'll tell you what the answer is. We plug in -1 for the first point, which is there, and then the second point, 2. We should get a slope of 4. So is it all right if I let you do that on your own? Plug in -1 and 2. Yep. A is going to always be the number to the left on a number line. And that last example, C, I'm just going to make a note about this. Okay, so that's what they give you for part C. Some of this, when you look at it, can be somewhat confusing. You may look at it and be, what is all that information? The only thing that you care about is the x value. This is your A, this is your B. And then you just go through and rewrite and do the formula. This right here is the function's value at -1. So this is what you get if you plug -1 in the function, which would be your y coordinate. So, any questions? That's pretty straightforward, right? There's not a lot going on there. All right, and then we have the difference quotient. So that's what we talked about last time, right? So for this one, I think I'll do one of these. I won't do them all. If we were to take f of x is x squared plus h plus x plus 1, and I want to find the slope of the secant line. So there's some language here, some terminology here. If you take a function and you connect 2 points and you draw that line, this is the slope of this line is known as the average rate of change, right? But it is also known as, this is the secant line. And so the slope of this secant line is given by the difference quotient. But it's the same thing as the average rate of change. It's two different languages, or two different descriptions of the same thing. So for this one, they're saying find the slope of the secant line. So the slope, we use m for slope, right? Sometimes what we'll do is we'll write SEC below it. That lets you know it's the secant line. That's helpful in Cal 1 because you'll also be looking at the tangent line, the slope of tangent line, which is something different. So you'll put m with the little TAN underneath it so you can distinguish between the two. The slope of the secant line, though, should be our difference quotient formula, f of x plus h minus f of x all over h. And what they want us to do for part A is they want us to pick for x1 and for h 0.5, right? So we're actually going to take 1 and we're going to add how much to it? X plus h. What would x plus h be? So this is the next point is 1.5, right? Just trying to show you geometrically what's happening here. All we really need to do is just plug things into the formula. So for us, with x being 1, which is what they give us for part A, this is 1 plus, what's h? 0.5 minus f of x, which is just f of 1, all over h, which is 0.5. Cleaning that up a little bit, before I plug in, this is f of 1.5 minus f of 1 all over 0.5. So you'll probably need a calculator now if you're going to plug 1.5 into the function. Unless you want to deal with fractions, what would you like? Do a calculator? Calculator? So go ahead and get your calculator out and plug 1.5 into this, and someone tell me what they get on their calculator. Y'all should start bringing your calculators, okay, just to have them. Anyone? Anyone?
Total of that?
Yes, 1.5 into the whole thing. 4.75? Okay. Minus, now plug 1 in, that you shouldn't need a calculator for. 3 over 0.5. So this is 1.75 over 0.5, which is on your calculator. What is it? 3.5. So that would be the slope of the secant line. Okay, so that picture right there is an actual depiction of what's happening. You have an x value, right? Your x value was 1. And then you added h, so h was 0.5. So this is your second point. The slope between those 2 points, right, the line, is 3.5. For part B, what they want you to do, you tell me, what does this mean? What are they doing by letting h be 0.1 instead of 0.5? They're moving that second point closer, aren't they? So if you do that, I'm not going to go through the computation. It would be at, where would the second point be at instead of 1.5? 1.1? Let's see what happens if I go to 1.1. See if I can get it. There we go. What's the slope? 3.1. Right? If you did the work. So we were at 3.5, right? We get closer, we're at 3.1. And then on part C, they want H to be 0.01, which is even closer. So let me move that even closer. I'm going to have to open this up. There we are at 1.01. What's the slope? 3.01. So we were at 3.5, then we were at 3.1, and now we're at 3.01. So what is our feeling? It's the closer we get to 1, right? The closer the slope gets to 3, right? But if I try and go right on top of it, my computer says indeterminate. Oh, shit, 1 over 0 encountered. Complex infinity. Ah, it freaks out. Because the computer cannot divide by 0, and that's what I'm asking it to do. But it makes sense visually to us that it should be getting closer to 3, right?
Yes.
Okay. All right, that's it for 3.3. Getting to 3.4 now. Y'all doing all right?
All right.
Ooh, look, old exams. Last semester's first exam. Hey, that's last semester's first exam. Analyzing a graph, solving an equation. We'll talk about that later. When is our first exam?
In a week and a half.
Week and a half? Yeah, we still got a ways to go. I'm going to pass around the sign-in sheet so I don't forget.
Right.
I'm sorry?
It's not next week. It's the following.
I think so. Not next week.
It's not next week. The following.
I think it's, yeah, I agree with you.
Something
It's on the back of that thing.
without pulling it out.
It's on the
16.
yeah.
Yeah, close, right?
Okay, this next section is going to go really fast. I have very few notes for this. As a student of mathematics and moving forward into pre-calculus and calculus 1, there is a toolbox of functions that everyone must have readily available to them. Meaning, you've got these functions, you know what they look like, you know the way they behave, you know their domains, ranges. So that when you get to calculus and they're like, oh, but this is just an absolute value function, we all know what that looks like, and you're like, yeah, I know what that looks like. Instead of like, I have no idea. So these are things that have to be memorized in terms of the visual characteristics. All right, and there are quite a few of them. I think there's 6 of them. I have all of them right here. So we're going to start with,
Quick question.
yes.
Before we take the test, are we going to see like that example of that test to kind of see?
I will give you something to go off of as a guide, yes.
Because I'm not asking for a review, I'm just trying to
Yeah.
guide.
I will give a guide, yes. Yeah. But the worst thing I could do for you is to give you like a review that looks just like the test for everything in here, because that's probably not going to happen in pre-cal. It's not going to happen in Cal 1. It's not going to happen in Cal 2. So you want to get used to preparing for an exam properly. How many of you feel like you come to class, you get it, everything's great, you do your homework, you're fine, you take the test. How many of you are in that boat, okay? So let me tell you a little bit about my opinion on that, all right? This is from experience, which I have quite a bit of experience when it comes to this. Anytime you feel like, you know what, I know this, I understand this, but when I go to the test and I crash, that means that you really don't know this, all right? It means you're about halfway, the way that you know some material is if you can explain it to somebody else, which is why I always encourage people to try and form groups and study together, because if you can help someone understand a concept, that means you understand it. So the reviews, right? The reviews, me giving you a review, what that does is it narrows your focus into one place. And then when something comes up that you didn't focus on and you don't know how to do it, then you're like, well, you know, I just froze. You froze because you weren't ready for something. You didn't practice enough. You didn't go and sit down. I mean, following me in class and being able to say, yeah, I understand that's not what this is about, all right? It's about you going home, doing your own problems, seeing problems I didn't do. How many of you have done a homework problem that I haven't shown? Okay? That's supposed to happen. It's not like it's possible for me to show you every type of problem here. Can you take the concepts from what we're talking about in here, can you extend them into a problem that don't have a direct connection to what I've said? When you can start doing that, then you're starting to grasp the material. If you need to see an exact example so that you can just mimic it, then you won't succeed as an engineer, you won't succeed as a computer scientist, because it's not about copying someone's process, it's about you knowing the process. Understand the difference? It takes time to mature as a student to get to that point. You know, I wasn't there definitely when I was in college algebra. I was still very immature as a student. But I've learned over time that, you know, what I thought at your level, what I thought was I knew it is far from what it means to know it. That makes sense. Okay. So the functions we need to know. First one, f of x is c. This is called the constant function.
What is x equals b? Does that also work?
B will work also. Yep. The only condition here, c is an element of the real numbers. Have you all seen that symbol before? Stands for element of. So if you have a function and the function is just a number, so when you graph it, it's a flat line, horizontal. I can move it up and down, right? So it can be at any height. The example of the function is right here in the corner. You see that f of x equals 5? There it is. It's 5 units high. It's a horizontal line. Sign-in's done. Anyone else need sign-in? Nope. And test is the 16th of February, which is a Tuesday, so that is not next week. That's a pretty simple function, isn't it? Just flat. Okay. The next function that everyone needs to know is f of x equals x. And not only do you need to know what it looks like, you need to know what it's called. The identity, right? So like in a calculus class, again, I teach calculus, so when I'm in there, I'll be like, oh yeah, you know, but if we just come in here and just look at the identity function, people are like, what? Identity what? What are you talking about? This is what I'm talking about, the identity function. It is the function f of x equals x. Why do you think they call it the identity? Or why do you think we call it the identity?
It's a simple linear function of f equals x.
f of x equals x.
Easy to identify.
Easy to identify. Because it reflects. Those are all valid answers. Ariel?
Is there an answer, like a specific answer?
I think there is. The answer that I'm looking for. I'm not saying anyone's wrong. I'm just looking for like what you're thinking. Okay, what if I plug in 3? What does it spit out?
3.
If I plug in 5? Negative 1?
Negative 1.
So my input is identical to my output. My output's identical to my input, right? It's identical, right? If you look at the ordered pairs for this, 2, 2, 3, 3, negative 1, negative 1, right? 0, 0. Input and output is identical. It's the identity. It doesn't change anything. Whatever goes in stays exactly the same, comes out exactly the way it went in. So this is your identity. It is a perfect diagonal. So like if you've learned anything about angles, right? The angle here is the same as the angle here. They're 45 degrees. 45 degrees between those. Okay. The next one we need to know, x squared. And this is called the squaring function. I know you're going to say that's a parabola, right? I've heard it called the parabola. Yes, it is a parabola, but f of x equals x squared by itself. That's it. No plus x minus 3, just x squared. Just like that. It's called the squaring. Squaring. What? Squaring? The squaring function. I'm going to draw these out here now, next to these. The squaring looks like that. So it looks like a U, right? It goes up, it has a lowest point. This squaring function has a local minimum, right? Also a global minimum. We talked about that. No global maximum. This is nice and smooth and curved, right? This is not like a corner. It's not a point down here. All right. That's your squaring function. They call it a squaring function because it squares the input, right?
Yes.
That's what it does. You put something in, it squares it. So I've drew a point here where it was on the origin, right? That point. Both of these graphs, the identity and the squaring, both have that point at the origin, don't they? And from here on out, the rest of the ones that we're going to look at all share that same point. This is the only one that doesn't share that, because if C is positive, it's moved up. If C is negative, it's down. If C is 0, we go through, yes. But let's look at the next one. What do you think the next one is? Squaring, cubing. So we call it the cubic function. Cubic. And we need to know what it looks like. Cubic looks like this. It has that point, doesn't it? 0, 0. The right side looks almost like the squaring function, although it's not the same. Okay, like if you put this one on top of this one, they're not the same function. And then on the other side, it goes down like that. Does that make sense to you why that would be true?
It's odd.
Because it's an odd, right? So here, if I plug in a negative or a positive, doesn't matter when I square it, they're both positive. Here, if I plug in positive, cube it, it's still positive. If I cube a negative, it's negative. So that's why it does that. We good? Square root. Square root.
Just call it square root.
Yep, just the square root function. And its picture looks, well, it does have that point, right? 0, 0 still there?
Yes.
And then it just goes out to the right. Why doesn't it have anything over here?
Because you can't have anything negative.
Can't plug any negatives in there, right? Okay, so that makes sense that it would only exist from here over. And then as you take square roots, you know, like the square root of 4, it would be 2, right? But then you'd have to go all the way out to 9 before you get up to 3. All the way out to 16 before you get up to 4. So it grows, doesn't it? But it's just slowly, right? Notice on all of these problems, all of these graphs, we could ask those questions. What's the domain? What's the range? Where is it increasing? Where is it decreasing? Local max, local min, right? All those questions would be valid for any of these. But we don't have the time to go through and say, what's the domain of this? What's it? Take too long. But you could do it for all of these.
The local max in the first one is every.
Pardon me?
I was just
Is every number? Is that what you said?
yeah, I said the local max in the first one is everything.
Yep. Okay, next one is cube root.
Every x value.
cube root. And as you might suspect, with the cube root, it looks a lot like the square root, except this time you can go negative because you can take the cube root of a negative number. So it goes like that. I'm going to write a little note here to myself. I just don't want to forget. I want to tell you about this. All right. Next one. One over x. That's an interesting function right there. It's called the reciprocal function. Interesting functions that we really study in depth in algebra classes or even calculus classes. 1 over x. And what makes it so interesting is that it's the first function that actually has some really serious domain problems, right? Like the square root has a domain problem, I agree. You can't do square root of a negative number. But this one, we can't plug in 0, right? But what would happen if we try and plug something really close to 0 in?
Like a super high number.
Super high?
Or super low.
Or super low?
Divided by 0, it can't be 0.
Oh yeah, or really
X can't be 0.
So let's try this. Look,
No, it would be really low.
this is one of these things that I struggle with my calculus students because it's something I assume they know, but for some reason it takes them a while. It's like midway through the semester they finally like click. So let's look at this function for a second. Let's do a t-table real quick. X, 1 over x. That's how we used to plot points, right? If I plug in 0, what? Undefined. Can't do that. So that means I will not have anything along the y-axis.
Can we also do that, like the 0 with the line through it?
That, no, because that would be saying input output, right? You have input is a number, then the function's going to throw output, right? You're saying that what's coming out of this is the empty set. That's kind of strange. Nothing comes out at all because the function can't even handle that. So, undefined. What if we plug in 1? 1, 2, a half, 3, a third, 10, a tenth, 100, 1/100th. So what's happening is I'm going further out to the right. I plugged in 1, I got 1, right? I plugged in 2, I got a half. I plug in 3, I got a third, right? I plug in 10, I got a tenth. 100, I got 1/100th. What if I plug in a billion? 1 over a billion. Is 1 over a billion a positive number or a negative number? It's positive. Very small number, right? Could I go out to a billion?
Yes.
Yes? 1 over a billion?
Yes.
Really, really tiny? Is it 0?
No.
No. Close to 0?
Yes.
What's close mean? Right, so now we're back in a relative, right? Now we're relative. It's all relative, right?
Relatively.
It's relatively close compared to how close 1 is. Yeah, your calculator will say 0 if you do that, but it's not. So what we do is we draw a dotted line this way, and we call this an asymptote. It's asymptote. You all heard that word before? Most of you who had high school math have seen this before, right? But it's been a while maybe. All right, so you have this, right? That means we're approaching it without actually touching it. So we're approaching this, never get there. And then if we try and go, we know we can't plug in 0. If we try and go, let's say halfway, like a half in there. Have a good one. Thanks for letting me know. Appreciate that. Okay, so if I plug in 1/2, that's getting closer to 0.
So that'd be 2.
1 over a half is 2. It reciprocates and becomes 2, so that means when I'm at half, I'm at 2. What would happen if I went to something closer like,
0.8.
yeah, I'm going to stick with a fraction because it'll be easier over there. How about 1/4? That's closer than 1/2? 1/4 is 4 now, right? So now I'm up here at 4. Here's 2. Now I'm already way up here.
Now you're just taking a reciprocal.
And now what?
1 over a billion is going to get you a billion.
Yeah, let's say I have 1 over 100. Let me go a little slower first. 1 over 100, right, is going to be 100, so I'm way up there. And so this thing is taking off, right? And this dotted line, the function cannot actually ever be anything at 0, can it?
No.
But the closer I get to it, the larger the function gets. So what we say is that this function blows up at this point 0. And in other math classes, we call it a singularity, if you've ever heard of that before.
Not in math class, no.
Not in a math class, but you've heard of a singularity before.
Yes.
See, like event horizon, is that what you said? Yeah, like event horizon is a point at which gravity becomes infinite. This is the idea of a singularity, is that you have a point at which your function is becoming infinite. Right? Do you see that? As you get closer to it, it blows up. But when you get there, the function doesn't have any definition to it. Is there a question? No? Okay, so now what would happen on the other side? Well, everything we would do on the other side would be exactly the same as what happened here, but because we're plugging negatives in, it's going to spit out negatives. So it's basically this picture, like reflected over, but twice. So it would look like this, and it would go towards this. See, there's a lot happening in this function. And it's important for a calculus student to have a good understanding of what it means by someone saying something like the following. Okay, let's see if you can handle this. Let's say I have a number, okay? It's fixed. And I divide it by something huge. What would happen? And when I say huge, I mean like almost infinite. I can't be infinity, right? But I can just get bigger and bigger. But this number on top is fixed. So someone give me a fixed number. Someone give me a fixed number.
10.
10, okay. The number on the bottom is huge compared to 10, like billion Googles.
11.
A virgin second.
What happens to this?
No, that's.
Is this number big or small? It's small, isn't it? This is approaching 0, isn't it? This arrow is going to mean approaching. Do you understand that? Fixed number, make the bottom denominator get big, the ratio gets small. What if I do it the other way? What if I give you a fixed number, I make the top get huge? What's going to happen?
Big number.
Huge number, right? This is going to become big. This will become infinite, won't it? Like grow without bound. Still with me?
Yes.
Okay, what about this? What if I take a fixed number and on the bottom I let something get really, really small? The number on the bottom is really small. The number on top is fixed. So give me a fixed number. 10. Divide that by 0.000000001. Is it what? Big number. That's a huge number. Understand that? What about this? Flip that one. Take a really small number. I'm doing it small. I'm writing it small because it's a small number. And divide that by a fixed. Divide it by a fixed number. So someone give me a fixed number. 10. Okay. On top of that, put 0.0000001. That's a small number. So this is actually going to head towards 0. If that's small enough, this will head towards 0. This huge, I can replace huge with infinity. These are very basic fundamental ideas in calculus. Because in calculus, you're not concerned about what's happening to a function at a point. You're curious about how a function is behaving. And so we need to understand this idea of, numerator gets big, denominator gets small. What happens? Did you hear what I just said? If the numerator gets big, denominator gets small, what happens? This number gets big while that number gets small. What's going to happen?
The number gets bigger.
It's going to be a big number. Right? What about the other way around? Small denominator over big numerator. Small numerator over big denominator. That number is trying to get small, right? You divide it by a big number, it gets even smaller. So this would be headed towards 0. This one would be headed towards infinity. I'm just giving you this because that first graph was the first time we can actually look at a graph and start talking about things like this. But it's foundation. I mean, this is basic but important stuff. All right. While I've got you thinking this way, what do you think would happen to this? If I have a number that's getting really big, okay, it's getting big, 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 and I take it and I raise that to a number that's really small. 0? Any other suggestions? 0? 0? What? Okay, what's 4 to the 0? 1. Right? 3 to the 0 is 1.
Oh, so it'd just be 1.
Well,
So it's going to get closer and closer to 1 now.
Right.
well, that's what we needed. That's what we would need to discuss in a calculus class. So I want to make sure we all understand.
We can go below 1.
This one right here, getting small means it's getting closer to 0. All right? This one getting close to 0. We know that anything raised to the 0 should be 1. Right? But this is a big number. And if we take a big number, it keeps on getting bigger and bigger. If you take a big number and raise it to a power, it should get bigger?
Not necessarily. If that power is greater than 1. If it's less than 1 but greater than 0, then it will be small.
What if it's like 0.00?
How about this? I'll make this even more confusing for you. Make that one get small. So let's say that this one wants to go to 0. Okay? 0.0000000, really small number, and I'm raising it to 0.00000.
Still small number.
Anything to the 0 should be 1, right?
Right.
But 0, or a number that's really small raised to a power, should get smaller or bigger? Are you confused?
Very.
You should be, because this is what the calculus is going to get into. You're going to have to work. You have to have a number sense with this,
Like it makes my
right? It's going to be a number sense thing that we don't ever really teach. Let's start talking about this being small. Let me just take an example. Is 1/10 small? Well, I don't know, relatively speaking. Raised to the 1/2.
That's going to be the square root of 110.
That's square root of 0.1, right? Sorry, square root of 0.1. That's what that would be.
So it's small.
So that would be
Smaller.
0.01. No?
Hold on.
What happens? If you take the square root, what times itself is 0.1?
It's like 0.31622.
So it's
766 something.
0.31.
3.1. So what happened there?
It's actually
It actually-
around.
Okay, it's all right. What happened though? It actually got larger, didn't it? Yes?
Because if it's 1/2, it's trying to get closer to 0, I suppose?
Yeah.
Well, closer to 1, I should say.
Look, I'm not trying to solve all of this right now. What I'm trying to get you to do, all I'm trying to get you to do, is realize that that graph that you probably have seen a million times has so many little things hidden in it that have to do with things like this. As something gets small, right? These ratios, how do these affect each other? And then later you get to something like this. Now let's do exponents. How do these work? And what it turns out in calculus is that every problem is different.